In this mini lecture, I'm going to talk a little bit about hyperbolas. The definition of a hyperbola, it's the set of all points in a plane, so in a flat surface, such that the difference of the distances to two fixed points is a constant. Now, that's similar to what we had for an ellipse, except this word difference was the word sum. So that's the only change in the definition going from an ellipse to a hyperbola. The two fixed points are called the foci of the hyperbola, just like I had the foci of an ellipse. And just like we did with an ellipse, there we represented the constant sum as 2a. Here we're going to represent the constant difference as 2a. We're going to start with a hyperbola that's centered at the origin. It has its foci evenly spaced from the origin along the x-axis, and we're going to represent the distance from the origin to each focus as c. Now, if we do that, we're going to end up getting a shape that looks like this. So these two curves are actually two different branches of the hyperbola. The one equation actually describes both of these curves as part of the hyperbola. And what I've labeled here then, or we've got this point xy that's somewhere on the hyperbola, and we've got these foci. So the center is at 0, 0. We move c to the left, so that's an x-coordinate of negative c. Or we move c to the right, that would be an x-coordinate of positive c. And we're going to take these distances from this point xy to those two foci. So one would be d2, one would be d1. And what we need is, if we subtract those distances, we need to get, so that would be d2 minus d1, that must equal 2a. To find distance d2 and distance d1, I'm going to use this distance formula that we've talked about before. So it's really just a matter then, we've got d2 minus d1 is 2a. To find d2, we calculate this distance. We subtract the x-coordinates, x minus negative c, and then we square that. Then y minus 0, and we square that. That's what we've got here. We add them together. And then we do the same thing for d1. It's going to be x minus positive c, and still y minus 0. And when we simplify, minus and negative becomes a plus. We get this equation. Like an ellipse, I'm not going to show all the gory details of this. We would move one of these radicals to the other side. We'd square both sides. There'd be a lot of algebra involved. We'd go from 2 square roots in the equation to 1 square root. We would get that square root by itself. We'd square both sides again, and we'd eventually get something that looks like this. What we're going to do is we're going to make a substitution. We're going to put in b squared instead of this difference c squared minus a squared, just to clean it up a little bit. And then divide by both a squared and b squared through all the terms, and we get this nice equation here. What we say then is that's the equation of a horizontal hyperbola centered at the origin. So x squared over a squared minus y squared over b squared equals 1. That's very similar to the standard form for the equation of an ellipse. It would be x squared over a squared plus y squared over b squared. So the only difference is it's a subtraction instead of an addition. So if it's an addition in between, we know it's an ellipse. If it's a subtraction in between, it's a hyperbola. It has to be equal to 1 to be in this standard form. The hyperbola itself, again, are these curved portions that extend to the left of negative a or to the right of positive a. So this box and these diagonal lines, those really aren't part of the hyperbola. The hyperbola itself is just this darker bluish gray curve on both sides. These diagonal lines that go through the corners of the box, those are called the asymptotes of the hyperbola. And what happens, the hyperbola curves away from the box and towards the asymptotes as I move to the left or right. We can verify some things about this graph by looking for the intercepts. So for the x-intercepts, that's where it's going to cross the x-axis, we would set y equal to 0. Because if I'm on the x-axis, I'm not going up or down at all. So my y-coordinate is 0. When I plug that in, 0 squared over b squared is just going to be 0. So we're going to get this here. The only way a fraction can be equal to 1 is if the top and bottom are equal. And so that gives me x equals plus or minus a. When I take the square root, I have to put in plus or minus. So those are those two x-intercepts that we see there. For y-intercepts, I would try letting x equal 0. Something very similar happens, of course. 0 squared over anything is 0. 0 minus something is going to be negative, but the problem then, if I multiply both sides by -1 here, I get y squared over b squared equals -1. That's a problem because if I have something squared, that's not going to be negative, unless I start with I, but we can't have I. There's nowhere for I on the graph, okay? So the problem is this left-hand side can't be negative, but it's supposed to be equal to -1. So what that tells me then, that tells me there are no y-intercepts, so the graph doesn't cross the y-axis. In fact, we can show, if we play around with the equation a little bit, that the graph cannot exist for any x-coordinates between x equals -a and x equals +a, which is why the graph stays, we could say, outside the box. Look at the graph here at the bottom. We've got this box that's going between a on the x-axis and b on the y-axis, and the graph stays outside the box, right? It doesn't go in between at all. If we took a hyperbola centered at the origin and we did the foci along the y-axis instead of the x-axis, we would get a similar result, except the hyperbola would open up and down instead of left and right. And so this would be the standard form. Also, for a hyperbola, we can't say whether a squared or b squared is greater. For an ellipse, a squared was always bigger than b squared, but that's not true for a hyperbola. For a hyperbola, a squared is what's always first. Also, the values of a, b, and c are related by this equation, b squared equals c squared minus a squared, which we had on that earlier page. Or if we rewrite that, we could add a squared to both sides. That would give me a squared plus b squared is c squared, or that's what I've got written here. I haven't shown a picture of a vertical hyperbola. That's going to be on the next page. So this is my hyperbola. The points where the hyperbola touches the box, so at this -a and at a, those are called the vertices of the hyperbola. The line segment that goes between -a and a, I can make that here in red. This line segment that goes between, that's called the transverse axis. If I would do the axis that goes between -b and b, perpendicular, going up and down, that's called the conjugate axis for this hyperbola. So here's the most general kind of situation with hyperbolas then. We have hyperbolas maybe not centered at the origin. So if they're not centered at 0, 0, if it's centered at hk, then the x squared gets replaced with x minus h squared, and the y squared gets replaced with y minus k squared. That's exactly the same thing that happened with an ellipse. So horizontal hyperbolas in general, this is what the equation looks like. Okay, x is first, horizontal. Okay, so again, you can't say whether a squared or b squared is bigger. Instead, a squared is whatever's first. So here x is first, a squared is under the x. This is what the graph's going to look like. This is my y-axis and my x-axis. My center hk maybe is over here. And this value a comes from the x. I move a left or right in the x direction. The b is with the y, so from the center I would go b up and b down. That would give me this box. I can draw the diagonals of the box. That gives me the asymptotes. The dotted box and the dotted asymptotes give me essentially a skeleton or a framework for the hyperbola. The hyperbola has to touch the box, whatever variable is first. For x, it's going to be on the x-axis. So it has to touch the box on the x-axis, well, in the x direction from the center. So we move left or right. We're not on the x-axis. We're up here at this point. And then the hyperbola always curves away from the box and towards the asymptote. That's going to happen for those graphs there. So again, the center's at hk. For the vertices, I move a left or right, so that changes the x-coordinate of the center to the left and right. The focus is a distance c away. So that would be this point here. I didn't label it. It was getting too messy. Okay. This would be h minus c k, and this would be h plus c k. All right. Notice for a hyperbola, then the foci are on the sort of the inside of the hyperbola, but that means the focus is farther away from the center than the vertex. So A is this distance. If I would look at the distance C, that would be this distance. And so I see here that C has to be bigger than A. So that's why I've got this result at the bottom. If C is bigger than A, then C squared has to equal A squared plus something. For an ellipse, it was the opposite. The ellipse was that oval shape, and the foci were on the inside, the vertices were on the outside. So there A is to the vertex, C is to the focus. There A was bigger than C, so the B squared had to be on the other side. The equations of the asymptotes, you don't really have to remember this, it's just the idea. Remember, we had y minus y1 equals m times x minus x1. And the x1 and the y1, that's just a point that the line goes through. Well, these asymptotes both go through the point hk, the center. So h goes in for y1 and k goes in for x1. I'm sorry, h goes in for x1, k goes in for y1. That's where this came from. The slope, the easiest way to find the slope is just to think about this box. What happens if you move from the center of the box to a corner? You have to go up B and over A, or up B and over A this way. One of them is a positive slope, the other is a negative, but for both, my change in y is B and my change in x is A. It's either positive A or negative A. So that's where this slope comes from. For a vertical hyperbola, the difference is y is first instead of x. Notice, though, for the center, I still have to look at the x term to get the x coordinate from the center. So this h becomes the x coordinate, though k becomes the y coordinate of the center here. And now my a is how much I move in the y direction, so up and down. B here is how far I move in the x direction, left or right. To get to the vertices, I'm going up or down in this case, so my y coordinate changes. For the focus, it would be the same thing. This would actually be k plus c up here for a y coordinate, and this would be k minus c. And the equations of my asymptotes, everything's the same except now my slope, I'm going up a and over b, so it's a over b instead of b over a. It'll be a little more clear when we do some examples. Finally, with a hyperbola, we do have some properties of hyperbolas that make them useful in sort of real-life applications. First of all, there is a reflective property, similar to what we had for an ellipse. The way this works is if I have a beam that's directed towards one focus, so that's this point B here, and this blue ray is being aimed at this focus. If it hits a hyperbolic mirror, the way it bounces off is it gets directed immediately to the other focus. So it gets redirected to the other focus in that sort of way. Hyperbolas are also used for navigation. So like I've said here, let's imagine we have a ship. It's out in the middle of the Pacific Ocean, and it's receiving transmissions that are sent at the same time from different broadcast locations throughout the Pacific Ocean. And there really is this type of stuff. Like the U.S. Navy has antenna on a bunch of different islands in the Pacific Ocean, and those are set up, synchronized, so that they all send out a pulse once every minute, I think it is, at exactly the same time. However, the ship is at different distances from those stations, so the transmissions are received at slightly different times. That's that difference, the constant difference idea. This allows the navigator to determine several hyperbolas on which the ship might be. The ship's location then is where the hyperbolas intersect. And I just grabbed this picture from the internet. I didn't make it. I don't know what it exactly means by slave stations and master station. But these hyperbolic lines, those are the possible places a ship could be. And so we wouldn't have all of these going on at the same time, but we would find where a couple hyperbolas intersect, and we know that's where the ship is. And finally, we have hyperbolic trajectories. So a body traveling through space, like a comet, for example, might pass through our solar system only once. In this case, the path it follows might have the shape of a hyperbola. So this red thing might be a comet coming through the solar system. When it's far away, of course, the comet is cold, everything's frozen, we can't see the comet very well. As it gets closer to the sun, things start to melt, ice and stuff, and it goes off as vapor behind the comet, and that's where we see the comet's tail as it goes around the sun. And then as it leaves our solar system, it gets frozen again and becomes less visible. Something like Halley's Comet that returns every, 76 years or something like that, it doesn't have a hyperbolic trajectory. It follows the path of an ellipse, which we've talked about before. So in that case, of course, it would be something like this. So most of the time it's way out here away from the sun, and it's dark and we can't really see it very well. When it gets close to the sun, that's when we see its tail, and then it goes back and away. But comets that return every so many years are following a path of an ellipse. A comet that comes through the solar system only once might be following a hyperbolic trajectory. It could also be parabolic. It sort of depends. And those are, we'll talk about parabolas in the next section.